In the 1930s, the physical world seemed remarkably simple. After decades of exploration, physicists believed they had reached the end of the map, identifying the few basic building blocks of all known matter. This was the standard model of the era. According to the data at the time, every star, planet, and person in the universe was constructed from just three components: the proton, the electron, and the neutrino. When researchers identified the Yukawa particle, now called the pion, it was framed as the final piece of the puzzle, a single particle needed to explain the force holding the atomic nucleus together. This sense of completion created a massive blind spot. By assuming the universe was a simple, orderly machine, science was entirely unprepared for the chaotic reality hiding just out of sight. That model failed in the late 1940s. Experiments observing cosmic rays began detecting V and K particles, entities that moved and decayed in ways that violated every established rule of physics. To study these anomalies, researchers had to stop relying on random cosmic rays and start producing them on demand, using massive new accelerators to intentionally smash subatomic matter together at near-light speeds. But their tools were insufficient. This is a cloud chamber, the standard detector of the day. Because it was filled with thin vapor, a high-speed particle from an accelerator could pass straight through it without hitting a single atom, leaving no record of the interaction. Physics faced a physical contradiction. Researchers needed a detector material dense enough to guarantee a collision, but transparent enough to allow for a high-speed photograph of the aftermath. Until someone could engineer a substance that acted as both a heavy target and a clear window, the next layer of reality remained invisible. In 1952, Donald Glazer proposed a solution that relied on the volatile behavior of liquids. He suggested filling a chamber with pressurized, near-boiling liquid hydrogen, using the liquid itself as the target. Glazer's design used a thermodynamic exploit. By suddenly dropping the pressure inside the tank, the liquid enters a superheated state. It is physically ready to boil, but lacks a point of origin to begin forming bubbles. This animation shows the transition. When a charged particle strikes the chamber, it tears electrons off the local atoms, creating a path of ionized matter through the liquid. Because this path is slightly more energetic, the superheated liquid boils here first. For a fraction of a second, the particle's invisible trajectory is replaced by a physical chain of microscopic bubbles, which can then be captured by a rapid flash photograph. Glazer had turned the laws of thermodynamics into a tracking system, forcing subatomic particles to leave a physical record of their own movement. These tracks only become useful when the chamber is placed inside a massive magnetic field. In this actual bubble chamber photograph, the field is what forces the particles into the distinct curves and spirals seen across the frame. The direction of a curve reveals the particle's electrical charge. Because of the magnetic field, positive particles are pushed one way, while negative particles curve in the opposite direction. By measuring the radius of these arcs, physicists can determine momentum. A high-energy particle will cut a nearly straight path, while a low-momentum particle is easily forced into a dramatic curve. As particles lose energy to the friction of the liquid, they lose the speed to fight the magnetic field, eventually collapsing into tight, inward-turning spirals. In many images, a disconnected V shape appears to begin out of nowhere. This indicates that an invisible, neutral particle, which leaves no bubbles, traveled through the liquid before decaying into two visible, charged particles. By converting these physical markings into coordinate data, researchers could finally determine the mass, charge, and lifespan of particles that were previously purely theoretical. The introduction of the bubble chamber at major accelerators led to an immediate surge in data. Instead of finding a few isolated anomalies, researchers began identifying hundreds of previously unknown subatomic entities. This handwritten ledger shows the scale of the change. Using chambers like Gargamel at CERN, physicists mapped out the lifetimes of strange particles, verified particle-antiparticle symmetry, and discovered neutral currents. The simplicity of the 1930s model was replaced by a reality so crowded that physicists began calling it the particle zoo. This overwhelming volume of evidence forced the scientific community to develop the standard model, a far more complex framework designed to bring order to the hundreds of new particles discovered in the bubbles. By the 1980s, bubble chambers were largely replaced by electronic detectors, capable of recording interactions at much higher rates. However, millions of the original photographs were archived without being fully analyzed. At the time, the manual labor required to measure every track was a mathematical impossibility. Today, researchers are digitizing these decades-old film reels and training artificial intelligence to scan the tracks. These algorithms are searching for rare decay patterns that were simply too subtle for human scanners to identify 50 years ago. While the boiling cameras of the 1950s have been dismantled, the records they left behind provided the evidentiary foundation for modern physics, offering the first clear look at a subatomic world that was far more populated than anyone had imagined.